Right, class, so maybe let's discuss together. I think most of you have done the two exercises. Now, the first one is the DFS. And in this case, you are given a graph. So, what we normally do, the first thing we do is to transform this into something that we can actually process, and that is either an adjacency list or adjacency matrix. So let's actually look at this, right? So now, to do this thing, if we use list representation, so first we have a list of vertices. So we have A, B, C, D, G, S. And A has two neighbors, B and C. B has one neighbor, D. C has two neighbors, D and G. D has one, G. G has no neighbor. And S has two, which are A and C. Now, this is an adjacency list, and when we process the DFS or the BFS, we are going to follow this list. So as we start the DFS, we say that we are going to start from S. So then we start from S. Now, S will then go on to a neighbor. So he has two neighbors, A and C. So we process the first one first, which is A. Now, we do it recursively. So then we go on to A. Now, A will go on to B. B to D. D to G. Now, G has no neighbor. So G returns back to D, which returns back to B, which returns back to A. Now, at this point of time, A has another neighbor, which is C. So then it's going to go and do C. Now, C has two neighbors, but both visited, so it will just return back to A, and then A returns back to S. S has only one other neighbor, C, which is already visited. So then the DFS is going to be over. So then the sequence that we're going to have is S, A, B, D, G, C. Okay, now some of you may have a different sequence if your adjacency list is different from what we put here. But if your adjacency list is exactly the same, then we expect you to get exactly the same sequence. All right? Yeah. Yes. Go ahead. Why do I choose A first before C? You mean this one, right? Now, in practice, when you are storing this graph, the ordering of the vertices in the list is up to you. That means that's not part of the information that is there in the graph. So whether it's AC or CA, both are correct, both are valid. Now, in practice, that is the case. For exam, usually to make it systematic, we will specify what is the order. And the most common one is alphabetical ordering. Okay, but the sequence of the vertices is not part of the information of a graph. So you can have it in any way. Any question there?
So if A and C swap position.
If A and C swap position, then you're going to do C first. Right, so S to C, then C to D, right? D to G. So then instead of that, you're going to have, okay, so let's actually do it, right? So if, in this case, the question is that if A and C switch positions, so then you have S, it will go to C, C will go to D, D will go to G, and G has no neighbors, returns back to D. D returns back to C. C has one more neighbor, G, but already visited, so C returns back to S. Then at that point of time, S can then go on to A. Now A then has two neighbors, B and C, right? So we'll do B first, but B will go on to D, D already visited, so B returns back to A returns back to S. Then your sequence will be S, C, D, G, A, B. Okay? So in this case, your sequence will be slightly different. This is S, C, D, G, A, B. This is S, A, B, D, G, C. Right? So what we usually advise you to do, first thing you do is to produce your adjacency list. Because if you don't produce exactly your adjacency list, we can't tell what is it that you're doing. Because you store it in any sequence, it may not actually be consistent. So first thing is to produce adjacency list, and then we're going to do DFS based on that specific adjacency list. Right? For the BFS, we're going to use the following adjacency list, the one that we did earlier. So the first thing we do is to visit the starting point S and queue it, so we get S. So the first DQ will take us S out of the queue. And then we're going to ask S, what are your neighbors? And neighbors are A and C. So we're going to visit the two in that sequence and enqueue them. So then the queue would then have A and C. Then the next DQ is going to take A out. A has two neighbors, B and C. C already visited. So only B is now visited and enqueued. So we get then C and B. Then we B has one neighbor. The next DQ is C. C has two neighbors, D and G. D is already, no, there's neither one of is visited. So we visit both of them, D and G. And then we enqueue them. So we have B, D, and G. Next DQ is B. And when B has only one neighbor, D, already visited. So we move on. We get D and G. We DQ, we get D. D only has one neighbor, G, already visited. So we move on. We get G. We DQ it. And G has no other neighbors. And at this point of time, the queue is empty. So then the whole BFS is over. So the sequence is going to be SAC, B, D, G. SAC, B, D, G. Now, if we revisit the idea before, that breadth first search is going to visit the nodes according to the distances. So S is the distance of 0 from itself, A and C are a distance of 1, B is the distance of 2, D is the distance of 2, G is the distance of 2. So then if you look at the way that is being visited, we see that the vertices that are closer to the starting point are going to be visited first by the BFS. DFS doesn't have this property. Alright, so that is for BFS. Now, so here there are a couple of things that we want to point out. So one, if you start from S, in this case, we happen to be able to visit all the other vertices. Now, what happens if you start from something else? So for example, if you start a DFS or BFS from G, what is going to be your sequence? Your sequence will be G itself, because that's the only vertex that you can start, which is a starting point, which is also the ending point, because there is nowhere else you can reach. So which means that for DFS and the BFS on the ground, you are not guaranteed to visit every node in the graph, right? So that's one. Now the second thing is that we talk about BFS using a queue. we talk about DFS using recursion. But earlier on, we also talked about recursion that can be simulated using another data structure. What is a data structure? It's a stack. So which means that when you look up DFS in various reference materials, in some cases, they may not be using recursion. Instead, they're going to have a very similar method to the BFS, except that you change the queue to a stack, and then it becomes DFS. So BFS with a queue, DFS with a stack.